Stoichiometry is the quantitative relationship among products and reactants. And I always think about cooking because that's in essence what cooking is. So if I think of maybe making, I'll jokingly say I have this 5-cup cookie recipe. This is not a real recipe. I'm just making this up, okay? It might work, but I'm just making it up. So it has 1 cup flour, 1 cup sugar, 1 cup chocolate chips, 1 cup butter, and 1 egg. Now, if any of you know anything about cooking, it's a whole lot of butter. But let's go through that again. 1 cup flour, 1 cup sugar, 1 cup chocolate chips, 1 cup butter, and 1 egg. And I'm telling you, it makes 2 dozen cookies, so 24 cookies. Okay? So if I went to my cupboard and I find I only have 1/2 cup sugar, and I don't want to go borrow any from the neighbors, and I don't want to go to the grocery store, but I have everything else, how many cookies could I make?
6.
Think again. It made 24 total.
Oh, 12.
12.
I
12.
didn't hear that part.
So it could make 12 cookies. So in other words, I have half of enough sugar, correct? I have half the amount of sugar that I needed to make the 24 cookies. So instead of making 24, I can make 12. That is stoichiometry. Does that make sense? The quantitative relationship among reactants and products. That's what stoichiometry is.
How do you plan on splitting the egg?
I knew you were going to ask me that, and I was hoping you would. How would you split an egg in half?
Don't tell me you have an egg. I said, don't tell me you have an egg in there.
No, I don't have an egg in half. Cough drop in here. Do you split an egg in half the way you'd split a cough drop in half? Nope. How would you split an egg in half?
Crack it on the table.
Say it again.
Crack that on the table.
Crack it on the table and then let half of it pour out on the table?
No, and then the other half pour it kind of.
Yeah, but then it would be yolk and white.
Mix it together.
Good job. Mix it together. Mix it together. Crack the egg in a bowl, mix it together, and then the volume of a large egg is usually about a 1/2 cup. And so you're looking at about 1/4 of a cup. Or, if you don't want to go that trouble, throw that whole egg in and be done. Find a smallish egg and put it in and be done. Wouldn't matter. But you get the gist of stoichiometry if you just think of it in that respect, okay? So stoichiometry is based on the law of conservation of mass. You can't have stoichiometry if the law of conservation of mass weren't true. You couldn't even, it doesn't work, it doesn't exist if the law of conservation of mass isn't true. And that law says the amount of mass going in is equal to the mass coming out. Okay, that's what the law of conservation of mass says. We have a balance in lab that gives mass, correct? Last lab, what did you do? What was one of the experiments that you did to prove the law of conservation of mass? What was it? Tell me the stuff that you used. You remember? What were some of the ingredients?
Oh, did we weigh like 2 test tubes? And
Yeah.
figured
What'd you do? You had 2 test tubes. You had what were the ingredients? Does anybody remember? Wasn't one of them lead 2 iodide? Is lead 2 iodide what you made? I can't remember. Yeah, it's lead 2 iodide is what you made. So what was it? Lead 2 nitrate, and I don't know what the other one was. You may remember?
0.5 0.5 like.
But you don't remember what the substance was? And I can't remember exactly what it was either. Bottom line, did you have substance A, clear colorless liquid, substance B, clear colorless liquid. You had a certain quantity of each. You had them in their test tubes, and you put the test tubes into a beaker just to hold them. Some people didn't understand that part. So you had those in a beaker just to hold them, and then you were getting the mass. After you got those in the beaker, you got the mass to see what the total mass of the unmixed, unreacted was. Then when you poured them together, you had a reaction occur. Was that a cool reaction or a duh? Was it cool? Do you all ever get like excited over anything besides the phone? I mean, did you get excited when you saw that? Did anybody say, wow, that is cool? I mean, I know my lab did. Some of you in my lab were like, oh my gosh, that is so cool. When you saw that happen, it's like as soon as they touched, what happened? You got that bright yellow solid. Come on. All around you is so much exciting stuff. Chemistry is exciting. When you pour those together, that should have been something that lit you up and said, how cool is that? And then when you put those empty test tubes, one of them was empty, one of them had the yellow solid in it, which was the lead 2 iodide. When you put those into the beaker again and got the whole mass, what was the mass? The same. So the mass didn't change. Did it seem like it might change when there was a solid? I mean, that solid seemed heavy, didn't it? I mean, it's a lead 2 iodide. That seemed really heavy, but it didn't change because it was still lead when it was clear colorless, just like it was lead when it was solid. And so that's what law of conservation of mass. Chemical reactions don't change the mass. The mass doesn't change with a chemical reaction. If we take numbers and look at the numbers mass-wise, then we're going to get the numbers equal at the end mass-wise. But that's not how we do a stoichiometry problem always. All stoichiometry problems aren't done with mass. The relationship that we use in stoichiometry is going to be a molar relationship using a balanced equation. So I want to go through. Down here at the bottom, we're actually going to be doing the stoichiometry problems. Up here, I want to just talk about something with you. So you've got a balanced equation. This is a simple balanced equation. And one way we could look at this balanced equation is to look at it from an atom standpoint. We could say this is 2 atoms of sodium. We could say this is 1 molecule of chlorine. Why do I call it a molecule? Diatomic, good. So we could say that's 1 molecule of chlorine, and this is 2 formula units of sodium chloride. That's what we could call that. But do I have the ability to really read the actual, can I see 2 formula units with my eyes? It's too small. I can't see formula units with my eyes. I can't see 2 atoms with my eyes. That's too small. So a better way to look at this is in a molar relationship. So this we call 2 moles of sodium, 1 mole of chlorine, 2 moles of sodium chloride. Now, if we're looking at it from a mole standpoint, can we go to the periodic table and get mass? So do I know the mass for 1 mole of sodium? What is it? 22.98 grams. The mass of 1 mole of sodium is 22.98 grams, or 22.99 grams rather. So a better way to look at this is in that molar relationship. So what this means is 2 moles of sodium reacts with 1 mole of chlorine to produce 2 moles of sodium chloride. Now if we look at it from that standpoint, so 2 moles of sodium react with 1 mole of chlorine to produce 2 moles of sodium chloride, that doesn't look like it works because 2 plus 1 doesn't equal 2, does it? But is the law of conservation of mass called the law of conservation of moles? No, it's the law of conservation of mass. So I'm going to prove that this is correct. 2 moles, I'm going to skip this sentence here, just come down here for a minute. 2 2 moles is 22.99 grams per mole. So what is 22.99 times 2? 45.98? Talk to me. Some of you have a calculator out. Okay. So that's 45.98 grams. 1 mole of diatomic chlorine is 70.90 grams. Why is that true? Why is it 70.90? It's chlorine. Why is it 70.90? Diatomic. It's diatomic. So it's chlorine that's Cl2, so it's 70.90. So 45.98 grams of Na plus 70.90 grams of Cl2 equals 116.88 grams. Add those together, confirm that for me. If you can do it in your head, that's fine too. Okay, that's correct. All right. Add up 22.99 for sodium plus 35.45 for chlorine. What do you get? 58.44? Is that what you get? 58.44? So 58.44 grams per mole, but how many moles do we have? 2. What's 2 times 58.44? 116.88. So does the law of conservation of mass work? So in other words, the moles look like they're off, but is the mass correct? The mass is correct. Now here's the problem though. Do I go to the lab every time and want to make 116.88 grams of sodium chloride? Is that how we're going to make every batch? I mean, is that true when you cook? No. If you make cookies, do you sometimes double the recipe? Do you sometimes triple the recipe? Now, typically though, we don't say, I want to make 1 cookie. How many ingredients do I need? What do I need to make 1 cookie? We don't do that, do we? We don't do that. But in chemistry, could we do that? Could we say, I want to make 1 gram? Then if that's true, how are we going to do that? How are we going to do that? How would we do that? Well, that's where we actually do the stoichiometry, an actual real problem. So let's go back. Using this method of mole relationship, we can form mole-to-mole ratios. And it's the mole-to-mole ratios that we will use to get us from one substance to another substance. And that's how we'll do an actual stoichiometry problem. So what we can say is that 2 moles of sodium equal 1 mole of chlorine. Now that's confusing because you're like, 2 moles of sodium mass is not the same as 1 mole of chlorine's mass. And I agree, it's not the same. It's not the same mass. But is it a ratio for this balanced equation? Yes, it's a ratio for that balanced equation. The ratio is based upon this balanced equation. So what is the ratio? 2 moles of sodium equals 1 mole of chlorine. Is that correct? 2 moles of sodium equal 2 moles of sodium chloride. 2 moles of sodium chloride equal 1 mole of chlorine. Yes. Now some of you are still like, but that's not right. It doesn't really equal that. Okay, and I agree with you. I totally agree. It doesn't seem like it makes sense. So here, I'll do something goofy. All right, how many people are back here? All right, how do you know, besides the fact that you saw me walk back here?
I can see your legs.
How many legs are there, Lucas?
2.
2. So 2 legs equals 1 person?
Yeah.
What do you see now?
Hands.
How many hands?
2.
2 hands. Do 2 hands equal 2 legs?
Yeah.
Does that make sense to everybody? I'm hearing Lucas. Am I hearing anybody else? Do 2 hands equal 2 legs?
Yes.
Okay. 2 hands equal 10 fingers?
Yes.
What do 10 fingers equal?
2 legs.
What else could they equal?
2 feet.
10 toes, good.
2 eyes.
2 eyes, good. You're getting it, Lucas, good job. Could they also equal 1 nose?
No.
So you're saying 1 nose equals 10 fingers? Yes, because it's a ratio. If you had seen 6 legs up there, then that would have automatically told you how many people were there.
3.
3. Does 3 people equal 6 legs? Yes. Ratio-wise, yes. 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 I didn't say 6 legs have the same mass as 10 fingers. But do they equal each other for a ratio? Yes. And that's what we're doing. That's why the mole-to-mole ratio works. That's why it works. So, go to the problem. These are, now, this information is just to kind of explain it. You're not going to have to ever do this. You do need to know the ratios. We're going to use the ratios. So now, I'm giving you this balanced equation. 2 sodium plus 1 chlorine yields 2 NaCl. We're going to use that balanced equation for these 2 problems. And I'm going to note this. It says this problem is very similar to gram per mole problems. However, you are now converting from one substance to a different substance. In all of those other problems, and I know that's been a while since you've looked at these, but let's just go back for a minute. Down here, this was when we did gram per mole problems. How many grams are in 3.50 moles of barium? The whole problem was talking about who? Barium. And this one, the whole problem was talking about who? Sulfur. So we didn't need a mole-to-mole ratio because the whole problem is talking about sulfur. But do you see how we changed gram per mole, gram to mole? The same thing is going to happen, except now we have a mole-to-mole ratio. So it says how many moles of chlorine are needed to react with 31 grams of sodium. So who's our given? Who's the given? 31 grams of sodium. So 31 grams of sodium. We need, honey. You can have some of mine if you'd like. You can go to the bathroom too if you need to. So 31 grams of sodium. So 31 grams of sodium is the given. What are we trying to find? Who are we trying to find? Moles of chlorine. So we're in grams. You have to go from grams to moles in order to use the mole-to-mole ratio. You must be in moles to get to the mole-to-mole ratio point. So how do we get grams to moles? How do you get grams to moles? 22.99 grams on the bottom. What goes on top? Where does that come from? So 22.99 grams on bottom, 1 mole on bottom, and who is this? This is of sodium. Where does this come from? Periodic table. That came from the periodic table. Yes or no? So grams cancel. I'm in moles of sodium. Who do I want to be in? Moles of chlorine. So what's my next step? That's the new step. Mole-to-mole ratio. This is the mole-to-mole ratio. So mole to mole ratio from balanced equation. EQN is balanced equation, or EQN means equation. So go up to the equation. How many moles of sodium? 2. 2 moles of Na. What are you trying to get to again?
1 mole of chlorine.
Chlorine. So here it is, 1 mole of chlorine. So 1 mole of Cl2. So moles Na cancel out, and look who you're in now. Are you in moles of chlorine? Talk to me. Does it make sense? What's the only new thing? Mole to mole ratio. It's the only new thing is the mole to mole ratio. And where does the mole to mole ratio come from? Balanced equation. It comes from the balanced equation. That's where it comes from, and that's the only new thing. So plug that in. And significant figures. How many significant figures do you have? How many significant figures? 3. Good. So what's my answer? 0.674 moles Cl2. Yes or no? Now, look at the problem again. Dissect it. This was what was given to you. It is in units of grams of sodium. You have to pay attention to who you are. This is like having identity change. You're sodium now. You don't want to be sodium. You want to be chlorine. And you want to be moles of chlorine. That means you must use this mole to mole ratio to get into moles of chlorine. But in order to get into the mole to mole ratio point, you've got to get into moles of sodium. Okay? So kind of talk yourself through that. Now, I'm confident if you understand this, you can do anything else at this point. And I'm kind of throwing at you a much more complicated problem second. It's no different than what you've all done all semester, though. It's just putting it all together. The middle part is the mole ratio. That's the new part. What's the starting point here? To who? Tons of who? NaCl. So 2 tons NaCl. It's a long problem. It's not a hard problem. It's a long problem. What's going to be the magic step to this, as with all stoichiometry problems? The mole to mole ratio. The mole to mole ratio has to be somewhere in the middle here. The mole to mole ratio is like the intersection. It's the interchange. It's the roundabout. It's the place where you start going the other way with who you are. That's what that is. So you're in tons of NaCl. What are you going to get NaCl into? Eventually, sodium. But you can't do that until you get into what? Who do you have to be in to get from one substance to another? Moles. You have to be in moles. But in order to get to moles, what do you have to get to? Grams. And that means you've got to get tons to grams. So what do you have to do? Tons to pounds, pounds to grams, then grams to mole, and then mole to mole ratio, and then keep going back to who you're going to. So tell me what to do. So 2,000 pounds in 1 ton. This is NaCl. Ton cancels. I'm still in NaCl. I'm in pounds now. Keep going. What's my next step? Say it again. How many grams in a pound? 454. So 454 grams of NaCl in 1 pound NaCl. So now I'm in grams of NaCl. Grams to moles, good. How many grams are in a mole of NaCl? 58.44. So 58.44 grams for every 1 mole of NaCl. Good job. Grams cancel. Moles of NaCl. Now, if I had a little bell, I'd go ding, 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 ding. This is the magic step. Why is this the magic step? Mole ratio. This is where you get to change who you are. Why? You're in moles. So what's my next step? 2 moles of NaCl go where? 2 moles of NaCl go on bottom. I'm now no longer NaCl. Who do I want to be? Who do I want to be? Sodium. So what goes on top? 2 moles of Na. I don't want to be moles of Na. I want to be what? Pounds. So I want to go moles of Na to grams. So how many grams in a pound? Or I'm sorry, how many grams in a mole, rather, for Na? So 22.99 grams of Na for every 1 mole. So I'm grams of Na, and I don't want to be grams, I want to be pounds. So what do I put next? 1 pound Na equals 454 grams. So grams cancel. Now, I tend to cancel out the 454s just so I don't have to plug them in, and I'll cancel out the 2s just so I don't have to plug them in. You don't have to do that. It's up to you. How many significant digits do you need in your final answer? 2. What do you get on your calculator? 1573.57, yada yada. So how do I round that? Go ahead. Come on. How do I round it? 1,600 pounds Na, or 1.6 times 10 to the 3rd pounds Na. Either way is fine. Now, let's go through here and label what you have. I think it's helpful to label this, especially for those of you that use your notes to study with, which I hope you all do. This is the given. That's the given. This is just a conversion factor you should have known from the past. Again, conversion factor that you should have known from the past. This is periodic table information. This is mole-to-mole ratio. And where does it come from? Balanced equation. That's where that comes from. And then this again is periodic table. And this is a conversion factor. Now, something that you also might put here where it says balanced equation is these are coefficients from balanced equation. So later when you've slept and you don't know where in the world I got the 2 and the 2, if you write this in here now, then when you come back to look at it, you'll be like, oh, coefficients from balanced equation. Here's the balanced equation. Oh, yeah, that's why she underlined those. That's where that came from, up there, okay? And that way you're kind of teaching yourself. Yes or no? Okay. All right, flip it then. right? Now, I've made this one a little easier in the sense that I've given you the molar masses already. On your test, oftentimes, if on a stoichiometry problem, I will give you the masses like this. If I give them to you, use them. Don't not use them. Don't go calculate it yourself. If I give it to you, use what I gave you. I'm trying to make it easier for you, okay? So if I give you these molar masses, use them. If you need to use them, okay? All right, so it says, what mass of CO2 is produced from 2.5 moles of oxygen and plenty C6H12O6? Do I need to worry about the plenty? That's saying I've got enough. Don't worry about it. That's what that's saying. You've got enough. Don't worry about it. So what's the given? 2.50 moles of who? O2. So 2.50 moles of O2. All right. Now, what are we already in? Moles. What's my automatic next step? Mole to mole ratio. I don't need to change. Once you're in moles, you're in moles. So be in moles. That's your mole to mole ratio point. Who do you want to be in? CO2. So find your moles of O2. What is it? Go ahead, say it. You're right. 6. So 6 moles of O2. What are you trying to find? Who? CO2. So what goes on top? 6 moles of CO2. But it doesn't want moles of CO2. It wants grams. So how many grams are in a mole of CO2? I've given it to you. What is it? 44.01 grams of CO2 in every 1 mole of CO2. So moles of CO2 cancel, and I cancel those 6's. You do need to write them. And on my calculator, I get 110.025. How many significant digits should I have? How many? 3. 3. 2.50, so 3. So what's my final answer? 110 with a decimal grams CO2. Easy enough? Does that make sense? All right, you do the next one. And the next one. See if you can do these last 2. Do both of these next two. Do both of them. Guys, the masses are here. The masses are here. Remember, you don't have to go look them up. They're right here. All right, let's look at the first one. I think some of you are struggling with the second one. Let's look at the first one. So it says, how many moles of carbon dioxide are produced when 0.297 moles of water are produced? So what's my given? 0.297 moles of water. Are we in moles? What's the automatic next step? Mole to mole ratio. Don't go to grams when you're in moles already. Don't go an extra step. So we go to the balanced equation. We're in water. Find water. What is it? 6. 6 moles of H2O. Who do I want to be? Moles of carbon dioxide. There it is. 6 moles of CO2. Moles H2O cancel out. Those 6's cancel out, guys. You can't get any easier than that. Yes or no? Yes or no? Did we get that? Okay. All right, the next one is really very similar to the harder one we did, second problem we did today. Did you go back to the other page and look? It's basically the same thing, except it's not dealing with tons. It's dealing with kilograms. So what's my given? 2.57 kilograms of O2. Why is it O2? Good. Kilograms converts to what? Grams. How many grams in a kilogram? 10 to the third. So 10 to the third grams in 1 kilogram. Whoop, looks like 1 kilogram. So that's O2. Kilograms cancel. So we're in grams O2. What do we want to be in? Pounds. We know we were in kilograms. We don't want to be in pounds of any of O2 at all. We want to get O2 into what? Moles. Have to get it into moles in order to do a mole to mole ratio. You always have to get into moles. You have to get into moles. You have to be in the middle in moles. So how many grams are in a mole of O2? 32.00 grams for every 1 mole of O2. So grams of O2 cancel. You're in moles of O2. You do moles of O2 to what? Moles of who? C6H12O6. So 1 mole, or that's not right. 6 moles of O2 on bottom. That gets us out of moles of O2. And it's 1 mole of C6H12O6. That's glucose, by the way, if you wondered what that is. That's blood sugar. All right, you're in moles of C6H12O6. We want to be in what? Grams, and then grams to pounds. So how many grams are in a mole? 180.18 grams of C6H12O6 in 1 mole. Moles cancel. And my last step is what? So what is that? 454 grams in 1 pound. C6H12O6. Did you have that set up? So plug it in. And how many significant digits do you use? How many total? 3. So what's my answer? 5.31 pounds, C6H12O6. All right, talk to me. Does this make sense to you? Lucas? Are you asking how to plug it in the calculator? Speak up, honey. Well, you always have to get into this mole-to-mole ratio. This is the key. You've got to get there. So whatever it takes to get you here, in other words, you started in kilograms, how are you going to get to moles? You've got to get to grams, gram to mole to mole. And then, where are you going from here? You're trying to get to pounds. That's the mole-to-mole ratio, though. Right, that's why I say the key, this is like the key step. That's the climax of the problem. What else? What other question? Okay, now the next part of this is limiting reactant stoichiometry, which is, what if you don't have enough of something? In other words, in our little silly cookie recipe story, what was my limiting reactant? Sugar. Half of a cup of sugar was my limiting reactant. Could I make 2 dozen cookies? Could I make 2 dozen cookies in my story earlier today? No, because I only had enough sugar to make what? 1 dozen. So was my sugar the limiting reactant? I could have had 5 pounds of flour. So I had excess flour, plenty of flour. But do I base the number of cookies I can make on what I have plenty of? Or do I base the number of cookies I can make on which one is limiting? It's whichever one was limiting. That's the one that's what I have to use, is whichever is limiting. And so in that situation, when you have a limiting reactant problem, your product is limited by the reactant you have that will produce the least amount of product. You cannot say that your product is going to be whichever of your reactants you have the least amount of. Does that make sense? In other words, you could have 10 grams of something and 10 grams of something else, but until you know how much each of those produces, you don't know which one is the limiting reactant. So let's look at an example. It says, how many moles of aluminum chloride are produced from 2 moles of aluminum reacting with 2.25 moles of HCl? Now, just looking at this, does it look like you have less aluminum than you do hydrochloric acid? But that doesn't necessarily mean anything. Just because the starting amounts are what they are, you don't know how much product's going to be formed, so you have to do 2 problems. And it says, limiting reactant stoichiometry, how do you know you have it? You'll have 2 or more reactants given. That's how you know. Solve for the same product for all reactants. So you're going to solve two problems. You have to solve two problems. The answer will always be the smallest amount of product formed. It's the smallest amount of product formed. And the limiting reactant corresponds to the smallest amount of product formed. So, set this up as two problems. You have to do two problems. So one problem is 2 moles of aluminum. The other is going to be 2.25 moles HCl. Now, I've made this one short for you because we're just going to moles. So it's 2 moles of aluminum, balanced equation, what goes on bottom, for my mole to mole ratio, 2 moles of aluminum. Who are we trying to find? AlCl3, so what goes on top? 2 moles of AlCl3. Okay, so moles of Al cancel and those 2's cancel, so golly, the answer is still 2. 2 moles of AlCl3. We don't know that that's the final answer yet or not. Why not? You have to solve two problems, that's right. So, what goes on bottom? 6 moles of who? HCl. Who are we trying to solve for? AlCl3, so 2 moles of AlCl3. Moles, HCl cancel. And what's your answer? 0.750 using proper significant digits. You have to put the 0, 3 significant digits, moles AlCl3. So now, what is the answer to the question? How much again? I'm sorry, say it again. I'm hearing two different. The smaller one. This is your answer. This is your answer. This is your answer. You do not add them together. You do not add them together. This is your answer. This is your answer. The smaller one. Now, before you flip your page, I want you to write something or at least think about something. What is this problem doing? What is this problem doing? What's happening in this problem? It says 2 moles of aluminum reacting with 2.25 moles of HCl. 2 moles of aluminum plus, in other words, 2 moles of aluminum plus 2.25 moles HCl. That's what it's saying. You're mixing them together. Guys, in lab this week you did this, except it wasn't aluminum. What was it that you did? Instead of aluminum, what did you do? You did this exact thing in lab, except it wasn't aluminum metal, it was zinc metal. Do you remember doing that? You did zinc plus HCl. And what did you get? Zinc chloride and hydrogen gas. And that hydrogen gas did what? Popped. It burned. It exploded. Do you remember that? Those of you that in lab that did not get that to happen, you were not patient enough. That's probably what happened. I know that Mrs. Skipworth said that some people were not getting it, and it's because you weren't patient enough. And you have to be patient. We had one group in my lab yesterday that I tried it for them, and sometimes it just took more hydrochloric acid or more zinc, and then you had to be patient. And we finally got it, but it just takes patience. And you have to be careful when you're doing on the inverted test tube. You had to be careful and not let the gas escape. You had to make sure you held it really tightly with no gaps. And so this is exactly the same thing. So when 2 moles of aluminum reacts with 2.25 moles of hydrochloric acid, you're only going to get out 0.75 moles of aluminum chloride. Now let me ask a question. Are you going to have excess aluminum? Is there going to be unreacted aluminum? Yes. Yeah, there will be unreacted aluminum. How do you know? How do you know you've got unreacted aluminum? Say it again.
All I can say, because if we have 2 amounts of those, like, one of them is like,
If one of them is limiting, the other one must be excess. But look at your product formed. Look at the amount of product formed. You only are going to be producing 0.75 moles of aluminum chloride. But you had enough aluminum to produce what? 2 moles of aluminum chloride. Does that make sense? So you have quite a bit of excess aluminum, which means could you add more hydrochloric acid and it keep reacting? Yes. Does that make sense? So hopefully you're putting together what you do in lab with what you're seeing here. Hopefully. That's the goal. That's the goal, is what you're supposed to be able to do, is to say, oh, that makes sense, what I was doing in lab. And that's why when I'm saying yesterday in lab, some of you needed to add more hydrochloric acid, some of you needed to add more zinc. Our ratio was messed up. Our stoichiometry was messed up because we weren't actually doing masses. We were just throwing it in. Okay? All right. Flip the page. And it says, use the following balanced equation to answer the questions below on this entire page. And that says may be, may not be, limiting reactant. How are you going to know if they're limiting reactant or not? 2 givens. 2 givens. All right, so the first one. Is it or is it not limiting reactant? It is. It is. So do 2 problems. So do it. Do it. I'm going to be quiet. I'm going to let you do it. Okay, let's look at what you have. So 13 grams of aluminum hydroxide. What'd you convert grams to? Moles. Then you went moles of aluminum hydroxide to who? Moles of who? I can't hear you. Thank you. Aluminum sulfate. So 2 moles of AlOH3, 1 mole of Al2SO4 and then we needed to convert moles of Al2SO4 to what? Grams. Tell me what? Do I have it here? Do I use these numbers? Good. So 342.17 grams for every 1 mole Al2SO4, yes? Okay. And then the last step is how many grams in a pound? 454 grams in 1 pound, and that's Al2SO4. Okay? So grams cancel, run your numbers. And I'm actually going to go ahead and do the other one before I run both sets of numbers. So 10.6 grams sulfuric acid. Do I do the same basic setup? Okay. So in the first one, do you get 0.062794? So significant digits, we're not going to worry about that until the end. You can, though. Since we don't know which one's going to be the final answer, it probably is best to go ahead and write it in proper significant figures now so you don't forget. So that would be 0.0628 pounds Al2SO4. Does it make sense? Speak, Lucas, if you're trying to tell me something, honey. I can't hear you at all. Talk louder, honey. Then clear it all up and do it again. Clear it all out and do it again. This is 0.0271 pounds Al2SO4. Do you get those two numbers? Everybody get those or not? Sorry, I wrote that. Let me rewrite it. 0.0271 pounds. Why did I circle that one? It's the smallest one. That's the final answer. That's the final answer. Yes or no? Yes. Three sig figs. The 0 in front doesn't count.
And also, one more thing, also, when you're placing the molds in the second time, you don't know where you're going, but how come you didn't put two mold with a OH3 up there? And how do you mold that down?
Here,
Yeah, from there to,
this is not 2 moles. This is for 1 mole.
so you always do.
The molar mass is always per 1 mole.
Okay, never mind.
The only place I put the molar mole-mole ratio is in the mole-to-mole ratio spot.
That's where you have to put it.
That's where you put the coefficients.
Okay, that's fine.
Everything else is always for 1 mole.
That's fine.
Okay? That's a good question, though. A lot of people try to do that. Other questions on this? It's long. You have to pay attention. It's not hard, but you've got to pay attention to your stuff. Okay? All right. Now then, here's what I want you all to do. We only have the rest of these problems. It's 5 more problems to do. And then on the back side, I've given you information about your test. I want to show you something on Blackboard. I think I've shown you this before. I'm going to show you again. Okay? I want you to look at Blackboard with me. And I want you to see on Blackboard, and I'm going to keep it talking, but you won't be able to see Blackboard on here. Under extra practice worksheets, there are already problems for mole. Here's lots of practice problems for mole, gram, Avogadro number problems. Here's more problems. I believe these are dealing with empirical, right here, empirical molecular formula and percentage composition. These are dealing with equations. And then this is stoichiometry practice problems. And this is the answer key. And it does tell you there's an incorrect mass here, so you need to pay attention to that. Then if you scroll down, and I'm going to show you what this says. This says test 3 practice problems. All of this is not necessarily, let me confirm, is it? Okay, part of this is helpful for you all, part of it is not, okay? The mole part is going to be helpful for you. Balance the equations is going to be helpful for you. Stoichiometry is going to be helpful for you. Then it gets down here to gas laws. Ignore this right now. This is for future. This is not for right now. It was a worksheet I had, and I'm letting you use it if you want to use it. So this is something you can do later, but not for this test. You will not have gas laws on test 3. And there's the answer key, okay? So let me confirm you have access to that, but I'm pretty sure you do. So there you go, there's the extra practice. And then, like I said, there's test 3 right there. And if you look down, yep, actually there is more, that's what I thought. Keep scrolling down. Do you see down here where it says test 3, homework and keys? This is all even more practice. Even more practice, okay? So as far as the amount of practice is concerned on this test, you have more practice than you've had on any other test. You can boost your grade on this test if you choose to, but it means you've got to practice. I'm telling you this today because you've got this weekend, and then your test is next Thursday, okay? So I will see you on Tuesday.